I want to start by thanking the organizers of this conference. It's a real pleasure to be here. My first time in Marseille and my first time at this institute, and it's very lovely. This work is joint with Olivier Biquard. And I will start perhaps by defining a Kähler-Ricci soliton, because although it's a generalization of Kähler-Einstein metrics, still perhaps there are people here that do not see these too often. So a steady Kähler-Ricci soliton is a triple of a complex manifold, a Kähler metric, and a holomorphic vector field. Satisfying the equation Ricci curvature of omega plus the Lie derivative with respect to x of omega is equal to 0. And this, as I guess everyone in the room knows, turns out to be a nonlinear, I guess fully nonlinear, second-order elliptic partial differential equation in either omega or else in the underlying potential. You should think of these as generalizations of Ricci flat metrics. And the motivation is the Ricci flow. Well, perhaps there are several motivations. You can also think of there as being a motivation for a kind of generalized geometry in which pairs of omega and x, rather than simply omegas, are the variational quantity, and there's a point of view developed by Bob Hasselhofer that extends this, but our motivation comes from the Kähler-Ricci flow. So given such a soliton, if we let psi t be the one parameter family of diffeomorphisms generated by x, then we have that the derivative with respect to t of a metric gt, which is the pullback at each time, let's call it, I guess, omega t, of the original metric, satisfies that its derivative with respect to time is the pullback of the Lie derivative of omega, which is minus 2 times the Ricci curvature of omega t. And so each such steady soliton gives you a solution to the Kähler-Ricci flow, which moreover can be considered to be a fixed point solution, since the solution is not changing except by diffeomorphisms of the manifold. And conversely, you can make, you can go in the reverse and say, suppose you have a solution to the Kähler-Ricci flow, and it's a fixed point in this sense, and you can determine that such things are always steady Kähler-Ricci solitons. Let me remark also that there are such things as expanding and shrinking Kähler-Ricci solitons, in which, by analogy with Einstein metrics, I take some sort of other term here. In that situation, I might get an expanding or shrinking soliton. And these are also fixed points if you consider a wider definition of fixed points in which you also allow homotheties of the metric. Okay, so this talk will be about the construction of steady Kähler-Ricci solitons. And I'm very lucky to give this talk so late in the conference after we've heard the talks of Joanna, of Claudio, of Caroline. Our construction is a gluing method, and it's also a construction on non-compact Calabi-Yau manifolds, and therefore it unites several of the threads we've seen before. I want to explain briefly where this comes from. So let's just say the obvious things that one can say about the conditions for the existence of a steady Kähler-Ricci soliton on a manifold M. So the first thing you can see is that by taking cohomology classes, we have this equation, and this cohomology class is just 0. This is the first term class of the manifold. And this means that if M admits a steady Kähler-Ricci soliton, then M is Calabi-Yau. Secondly, I think this fact is due to Ivy, although it's not quite clear in the literature. Such a manifold M must be non-compact. So to be clear, I mean, I told you that Ricci flat manifolds are steady Kähler-Ricci solitons. So if I have something that's a non-trivial, that is not just Ricci flat, Kähler-Ricci steady Kähler-Ricci soliton, those are the ones that necessarily have to be non-compact. And thirdly, this is kind of obvious, but it must admit a holomorphic vector field. And in this talk, I guess I'll go through the first, relatively large family of such manifolds that we could come up with and explain how to find steady Kähler-Ricci solitons on such manifolds. I want to next list the known examples. Please.
Why is it non-compact?
So this is not completely obvious. I guess there's an argument that I think on some level rests on a Bianchi identity, but no, it's not clear.
And then you put in brackets or Ricci flat. That means if it's Ricci flat, you're okay.
That's right. So if the vector field X, let's say, is non-zero, I'm simplifying slightly, but if the vector field is not Ricci flat, then it has to be non-compact. The manifold is the metric, yeah. Okay. So the known examples before our work consisted firstly of an example of Hamilton in the 80s on C called the cigar soliton. And I'll draw a kind of schematic picture. It's something that is asymptotic at infinity to a cylinder. The vector field is radial like this, and it kind of curves in at the origin. Okay, I get to use the machine. Let's see. Secondly, so there's a family, or rather two families, constructed by Tsao in 1996. So the first family is on Cn, and the second family is on the bundle O minus n, its total space over Cp n minus 1. This second one is actually a one-parameter family. One parameter after rescaling and applying diffeomorphisms. And I guess this first example here, the n equals 1 case, is the cigar soliton, so it generalizes Hamilton's work. And finally, again generalizing these examples, there are more recent examples due to Dancer, Wang, and to Yang. These are, let's say, in the years 2008 to 11. The thing I want to remark about all of these known examples is that they are constructed by finding a way to reduce to a system of ODEs. So the typical construction is you find sort of a foliation of the manifold by hypersurfaces, then you look somehow transverse to those hypersurfaces, you have one parameter or one variable, and you consider a system of things about the metric, each in those one variable, and you end up with a system of ODEs, one function or two functions linked or three functions linked. But in each case, it's simply a matter of appropriately studying the family of ODEs with boundary conditions. And by contrast, the work I'll talk about today is the first known examples to my knowledge of solitons that are constructed actually by solving the underlying system of partial differential equations.
So does it mean that all those guys are kind of homogeneity?
Yes, that's right. I guess before I go deeper, I just want to mention that in the expanding case, there's been some very interesting recent work of Ronan Collin and Alex Darwell that does something similar in terms of using the sort of broad nonlinear techniques of complex geometry to find a very large family of expanding solitons. And there's a strong analogy with our work in terms of the underlying manifolds. So secondly, I want to work up to stating our result. And I think I can go relatively quickly through the stage of explaining what the underlying manifolds are, because we've seen these manifolds occur in several previous talks. They're, as I said, somehow the first large family of non-compact Calabi-Yaus. So the setup is that if we let G be a finite subgroup of SUN, such that it acts freely on Cn except at 0. And if we let N be an equivariant crepant resolution of Cn modulo this group G, then our construction produces Kähler-Ricci's, steady Kähler-Ricci solitons on such manifolds. I guess we've seen similar things already at several stages during this conference, but just to quickly review how these conditions work. So having SUN be the group inside which G lives means that Cn mod G is Calabi-Yau, because the holomorphic, the tautological holomorphic n form on Cn then descends correctly when quotiented by G. The condition that G acts freely means that Cn mod G has an isolated singularity at 0 and no others. The fact that we have a resolution by definition means that so there exists an identification, so more precisely a biholomorphism from M away from the inverse image of the cone point to Cn except for the cone point mod G, and this means that we can do almost all of our work on this manifold using the coordinates of Cn, and only occasionally discuss boundary conditions about what happens on the manifold on which these things really occur. And then having a crepant resolution means that M is also Calabi-Yau, and having an equivariant resolution, I mean, you should also listen to Claudio's point of view on this, but this condition ensures that the vector field, the radial vector field, X, which I will call minus, I think, 2r del by del r, from Cn lifts to the manifold M. And so the upshot of our collection of conditions is that we have all of the things we need satisfied. We have a Calabi-Yau manifold that admits a holomorphic vector field, and moreover, by construction, it's non-compact. So this is fertile ground for the possible existence of a steady Kähler-Ricci soliton. Next, I mean, although I think that we've essentially seen this information in previous talks, I just want to run through the examples of such manifolds, which roughly becomes classifying the examples of such groups. So let's see, we can take as a very simple example G to be Zn. This is embedded inside SUN by e to the 2I pi, let's say, k over n times the identity matrix. This gives a subgroup of SUN. And then in this case, it turns out that precisely this manifold, the total space of the line bundle CP n-1, is naturally an equivariant crepant resolution of Cn modulo this group, which means that we can retrieve these examples of Sau as the simplest case of our construction. So let's see. Secondly, this is largely following the work of Klein in 1884. The finite subgroups of SU2, so this is the dimension 2 examples, come in 2 infinite families and some exceptional examples. And these all have a unique minimal, so-called, resolution. So the corresponding singularities, I guess, are called the Kleinian singularities. And the fact that these manifolds are Calabi-Yau, in fact, hyperkähler, has been known for a long time. And so in particular, this means that there are infinitely many examples of our construction in dimension 2. And then finally, by a similar argument, there are infinitely many examples of our construction in dimension 3. So in this case, I think the classification is due to Blichfeld in 1917. I believe there are 10 infinite families of finite subgroups of SU3. And then in this case, it was proved by, let's see, do I remember the authors? Reed, yes, indeed. Bridgeland and King, as recently, I think, as 2000, maybe in 1, that there is something called the G Hilbert scheme. So this is the collections of points in Cn, each related by the action of the group G. So the moduli space of such points suitably resolved according to the usual Hilbert scheme method, so this moduli space was constructed, which provides a canonical equivariant crepant resolution of C3 mod G. And in this case, there could also exist other crepant resolutions. These are not necessarily the only ones. Finally, in dimension 4 and higher, things become slightly harder. So I'm not sure, for example, that I know that there are infinitely many examples of our construction in each dimension from 4 and upwards. The main problem is that if you have a finite subgroup of SU4, for example, it's not clear that there exists a crepant resolution of the quotient of C4 by that group. And indeed, in most cases, there does not, but still you can construct examples where there is, for example, by the methods of toric geometry. So these are the underlying methods to our construction. And you've seen them before, the reason being that these are non-compact Calabi-Yau manifolds modeled on Cn mod some group. So you can also expect to find an asymptotically locally Euclidean Ritchie flat metric on such a manifold. This problem was solved 20 years ago by Joyce, following earlier work of Tian Yao, of Kornheimer, and many other people. So next I want to give an overview of our method. Please.
So the result is, I don't think you stated it. The result is that all these have...
Yes, in fact, that's an excellent idea. I will state my result. What a wonderful idea. Sorry, it's much more fun to talk about other people's work than your own. Okay. Thank you. So our theorem okay. So is that if we let K be a Kähler class on M, which is an equivariant crepant resolution of such a quotient of Cn, then for all epsilon sufficiently small, there exists a steady Kähler-Ricci soliton in the class, let's say epsilon squared times that Kähler class, with associated holomorphic vector field, so the drift holomorphic vector field, X, where X is this lift of the radial vector field. So a point maybe on scaling, in case you're wondering how this works. So if I rescale a Ricci-soliton metric, I continue to get a Ricci-soliton metric, but the vector field changes. So therefore, by fixing as constant the vector field, I can compare correctly the Kähler classes in which we prove the existence of a steady Ricci-soliton metric. And for us, we prove the existence of such a metric in some sense all sufficiently small Kähler classes. All Kähler classes sufficiently close to the zero Kähler class, which you can think of as being the manifold C3 mod G itself. Yeah, let's see. Do I want to say anything more about the theorem? Yeah, okay. So this is a gluing construction, as you might guess, and maybe I'll tell you the geometry of these manifolds that explains where that gluing construction comes from. So firstly, as epsilon tends to 0, we can continue to identify almost all of these manifolds M with the quotient Cn mod G. And so we have that this metric, maybe I'll call it omega epsilon, converges to what I'll call omega plus. This is the Tsao soliton metric on Cn. And I mean, strictly speaking, I'm taking the quotient of that metric by G. And then on the other hand, as epsilon tends to 0, if I blow up that metric, then this converges after diffeomorphisms to omega minus, where this is the Joyce-Ricci flat metric on that same crepant resolution. And you can see that by rescaling in this way, I get metrics that are in a constant Kähler class, so this convergent makes sense. And this then tells us a great deal about the asymptotic geometry of our manifolds. So all of these, at the same time as these metrics as epsilon tend to 0 are converging to the Tsao soliton, we also have that for any fixed epsilon, the behavior at infinity of these metrics is closely asymptotic to that of the Tsao soliton. So this omega converges in spatial infinity exponentially fast, let's say, to the Tsao soliton. And this tells us sort of broad strokes things about the spatial geometry of these soliton metrics. They're asymptotic to a known soliton metric, so they have the same volume growth, for example. It has volume growth that the volume of the ball of radius r is asymptotic to r to the n. This is half the maximal amount because the dimension as a real manifold is 2n. So for example, taking the cigar soliton as the kind of first example of this construction, we have n equal to 1, a two-dimensional manifold which has volume growth linear, and the manifold itself is asymptotic to a cylinder. I'm going to, for the rest of the talk, when I draw pictures of our solitons, kind of draw them as curving in. You can, in some whatever sense, think of them as being parabolic. And then maybe I'll explicitly write the thing that I said before, that when the group is Zn, we retrieve the SAO solitons on the total space of the line bundle On. Okay. Yep, I think that was a good digression. So let me talk briefly now about the method. So as you can see, this family of manifolds has portions modeled on the Tsao soliton and portions modeled on the Joyce-Ritchie flat metrics. So I'll draw little pictures of them. This kind of parabolic thing, it's not really getting any smaller, so maybe that's more appropriate, is our orbifold equipped with the Tsao metric. And then we also have these known asymptotically locally Euclidean metrics on the resolution due to Joyce. And our construction consists of identifying some band like this, some band like this, shrinking this, attaching it here, and solving the perturbed equation. So there are many experts on this in this room. I guess Biquard, my collaborator, had previously been involved with Minerva in the construction of Ricci flat metrics by this method. We have people like Arezzo, Picard, and Singer that constructed a constant scalar curvature and extremal metrics by this method. To our knowledge, it's the first time that it's been done for Ricci solitons, but on the other hand, the people in mean curvature flow have also previously succeeded in doing gluing constructions for the solitons of mean curvature flow. So for example, Nguyen had some constructions like this, I think about 5 years ago. So let me maybe briefly describe how this approximate metric is constructed. So, as I said, we construct, I'll call it perhaps omega epsilon tilde. This is the approximate metric in the class epsilon squared k, which is an epsilon diffeomorphismed, epsilon meaning the diffeomorphism depends on epsilon, omega minus, rescaled, on the region z using the coordinates of Cn less than epsilon to the n over n plus 1, and then is equal to omega plus for z at least 2 epsilon to the n over n plus 1. So I didn't tell you how to do this, I simply stated that it was possible. see. Next, I will explain what equation has to be satisfied, reduced to an equation on potentials. So we first observe that there exists a moment map. It's in the manifold to R. Oh, I guess this is a tilde. A moment map in the sense that d mu is the moment map with respect to our approximate solution of the complex rotation of the radial vector field. And this moment map, moreover, satisfies that on the larger gluing region, it's equal to the moment map for the Sau soliton. And now we can construct the scalar equation being satisfied. So if we let f epsilon, the error term, be equal to minus the logarithm of the volume form of our approximate solution modulo the volume form that comes because we have a Calabi-Yau manifold from its holomorphic n form. And to this we add the moment map. Then it can be verified that if we let T epsilon be the operator omega epsilon plus I over 2 del del bar phi to the n over omega epsilon to the n minus e to the power of 1/4 x psi plus f epsilon, then zeros of this operator correspond to solitons. Okay, so perhaps I will not write down the proof, but in fact it's pretty easy. Perhaps the key part, as far as I'm concerned, is that if you have a moment map, mu epsilon, of the kind I've written down, then you can check that I del del bar of this moment map is equal to the Lie derivative of omega epsilon. So this provides a way of reducing the Lie derivative of omega epsilon, which appears in the Kähler-Ricci soliton equation, to a term mu epsilon. Okay. And then I should remark that this f epsilon, which we should think of as being the error term, is going to be equal to 0 on the set z at least 2 epsilon to the n over n plus 1, because we already have a soliton on this set. So we have f epsilon, which is a compactly supported error term, explaining how far our construction already is from being a soliton. And we're going to so that, I mean, I guess you can think then of T epsilon of psi perhaps being, T epsilon of 0 perhaps being quite small, and now we're going to find a psi near 0, which is actually a 0 of that operator. Okay, And next, we need to follow the gluing procedure already outlined by Claudio and by Caroline. We need to calculate the linearization of T epsilon this is 1/4 times the Laplacian of our approximate solution minus e to this error term times the vector field x. So this is where we start to see the slightly different geometry of this problem compared, for example, to the Kähler-Einstein problem. We have the vector field x, the thing that makes it a soliton rather than a Kähler-Einstein metric, appearing as a first-order term in the equation. And so in order to solve this problem, we need to understand the geometry of an equation like this with a drift term, with a linear term, and check that such an operator is invertible in the specific asymptotic setting that we're studying. So let's see. I think I will just briefly state the invertibility result. So first of all, I have to set up the Holder spaces in which I study invertibility. So let us let rho epsilon be a scalar function, let's say, which is epsilon in the small regions of the manifold, which is z in the neck of the manifold, and which is 1 in the large part of the manifold. And similarly introduce a family of weight functions, w epsilon, gamma, and delta, which are, in this case, epsilon to the gamma in the small portion, norm of z to the gamma in the intermediate portion, and e to the minus delta times the moment map in the large portion. And now we can define a Holder space, or rather a family of Holder spaces suitably weighted ck alpha epsilon gamma delta using this radius and these weights, so I won't write the full definition, but for example, the Holder coefficient is equal to the supremum over all z in the manifold of, I guess, the radius times the supremum over a ball of that radius of the Holder coefficient Okay, and so we have this family of Holder spaces depending on epsilon and also on two weights, gamma and delta. The key point being that these spaces change as epsilon changes, but in a controlled way. And then we can prove a linearity result, or rather an invertibility result for linearization. So for all delta in a certain range, and for all gamma in a certain range, there exists a constant such that for all epsilon sufficiently small, this operator, our linearization of T epsilon, from the space 2 alpha with those weights to the space 0 alpha with slightly changed weights is an isomorphism and moreover its inverse has controlled norm. So for all u in the original space, the norm of u is at most c times the norm of the operator applied to u in the range norm. Okay, and in order to prove this proposition, you need to prove it somehow in 3 limit cases: a limit case on this manifold, a limit case on this manifold, and a limit case on the conical neck connecting them. And I guess this case and the neck case are comparatively standard. People have done gluing problems with that kind of bubble before. What's less standard is developing the analysis to show that the limit operator on this manifold is invertible. And so in order to do this, you need the following identity, which we also proved. Let me see. Mystery identity. Okay, so the mystery identity is that e to the delta times the moment map times Laplacian minus x times e to the minus delta times the moment map is equal to minus 4 delta n minus delta times x times the moment map. This is taking place on the Tsao soliton, and the value of this identity is that it can be checked that this term here is consistently positive in the range of delta we selected, the range of delta between 0 and 1. And this means we have a barrier function which provides the invertibility of the model operator on the Tsao soliton itself. And then using a first order theorem like this proposition, we can apply an inverse function theorem to obtain the existence of solutions to this equation for all epsilon sufficiently small. I think I have 2 minutes left, so I'm going to, briefly outline the 2 natural generalizations that I see for the work that we've done. I think that there's a lot that can be done in this field, and the 2 things I'll state are just the most natural. The first generalization is to extend from resolutions of Cn mod gamma to resolutions of other Calabi-Yau cones. So this is the work that was done by Craig, for example, in the Ricci flat case. In recent work by Collins and Zakhalahidi, we have really nice understanding now of how to get Calabi-Yau cones, where they come from. And so there's a lot more manifolds that you could potentially produce small families of steady Ricci solitons on by a similar method, so long as you could understand an appropriate model here, perhaps just carrying over an adaptation of the Tsao soliton to those cones. The second open problem is to, unfortunately I erased our theorem, but our theorem applies only for sufficiently small elements of the Kähler cone to extend the same construction to all elements of the Kähler cone. So in the example that I stated at first, this is the Tsao example. Tsao found a 1-parameter family of solitons corresponding to the 1-dimensional Kähler cone, but he didn't have to stop for a small epsilon. He could do it for all epsilon. As far as we can see, there's no reason why you shouldn't be able to produce a steady Kähler-Ricci soliton in every class on these manifolds. But a gluing technique is no longer useful for this. It requires actually solving a Monge-Ampere equation. So I think there's a lot to be done in this field, but those are the 2 immediate open problems that I see. Okay.